This is a video, or not a video, slides, I guess, about discrete mathematics for section 5.6, binary trees, expression trees, and traversals. Done by Kenneth H. Rosen, I think you pronounce that. He's from Sylvia Sorkin Community College of Baltimore County. Anyway, got to give them credit. He did a pretty good job here. First of all, tree. We've already talked about this. Tree is a connected, undirected graph, no simple circuits. An undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. So which one of these are trees? A, B, and C? Well, A is, but B is not. There's a circuit. And C is okay. A and C are trees. Specify a vertex as a root. So here's the root. If we call that the root, then everything else one level down gets moved down away from that. If we tried to do that to letter A, if you call this middle one the root, then we've got to put these down. It's called a rooted tree. If you call something else the root, though, you have to also put those down. But it's of course sort of got to be, I guess, levels here. A different rooted tree because you picked a different root. So Jake's Pizza Shop is a tree. The owner Jake, then the next in command is the manager Brad and the chef Carol. Under Brad are the two waitresses, waitress and waiter. And Chef Carol has a cook and a helper, Max and Len. So this is also a tree. The tree root is owner Jake. The leaf nodes, when you get down to the bottom and it has nothing below it, that is a leaf. Level 0, level 1, level 2. The number of the level is really how far from the root it is. These are siblings of owner Jake. These have the same parent, owner Jake. These are siblings, but they are of the parent, manager Brad. And this is a left subtree, a right subtree. If you can make a tree out of something below it. A vertex that has children is called an internal vertex. A subtree at vertex V is the subgraph of the tree consisting of vertex V and its descendants, and all the edges incident to those descendants. So everything below it. So how many internal vertices? This is an internal vertex. These are the descendants, waitress, and the cook. A rooted tree is called a binary tree if every internal vertex has no more than 2 children. The tree is called full binary tree if every internal vertex has exactly 2 children. An ordered rooted tree is a rooted tree where the children of each internal vertex are ordered. They can be in whatever order you'd like, smallest to the left, largest to the right. We'll talk about that a little more later. 2 possible children of the vertex are called left child, right child, if they exist. Tree properties. Okay. A tree with n vertices, n minus 1 edges. At most 2 to the h leaves in a binary tree of height h. Remember, the height is how far away you are from the root. If a binary tree with L leaves is full and balanced, then its height is log base 2 L. I guess I should have tried to show you how we got up to that, but you guys remember your mathematics. This is 2 to the h up here for theorem 5. Well, this says 2 to the h is equal to L. So an ordered binary tree. Everything to the left is lower than the parent, and the parent is lower than the child, the right child. Here, Ken and Joe. If we put in something that's an I, started with an I, you'd come to Lu, you'd say, okay, I is less than L, but I is greater than H, and I is less than K, and I is less than J. So I would go to the left down here with Joe. The parent of a non-root vertex is the unique vertex U with a directed edge from U to V. That's a little confusing, directed edge from U to V. So I guess this, let's go back. The parent of a non-root vertex is anything besides the root. Unique vertex with a directed edge from U to V. So, from U to V, from U to V. So this is the parent. This is the root, parent, parent, root, I'm sorry, parent, child, left child, right child, left child. A vertex is called a leaf if it has no children. So Ed is a leaf, Joe is a leaf, and Ted is a leaf. The ancestors of a non-root vertex are all vertices in the path from root to vertex. Okay, so as you go down the path, Ed's ancestors are Hal and Lou, but not Ken. Got to go to the root. Ted's are Sue and Max and Lou. The descendants, not ancestors, of a vertex are all the vertices that have V as an ancestor. Okay, so this is a little bit bigger because if this is an ancestor, all of these down below have Lou as an ancestor. Does that make sense? Ken has Joe. Hal has Ed and Ken and Joe. The level of vertex V in a rooted tree is the length of the unique path from the root to V. So, Ted, from the root 1, 2, 3. Ted's in level 3. This is level 1. The root is level 0. Here's 2 and here's 3. So if you draw it nice, you can see the root levels. The height of a rooted tree is the maximum of the levels of its vertices. So this is 3. A rooted binary tree of height h is balanced if all of its leaves are at levels h or h minus 1. So is this balanced? At h, the height 3 or h minus 1. And that is true. Let's go back. It's balanced with height h if all of its leaves are at h or h minus 1. h3 or 3 minus 1, 2. So this is balanced. The goal in computer programs is to find any stored item efficiently. So they use a binary search tree. It can be used to store items and its vertices. It enables efficient searches. So as you store things, you put them in order. That way you can look for them quickly. A binary search tree, BST, is the best for a lot of this stuff. Special kind of binary search. Each vertex contains a distinct key. The key values in the tree can be compared using greater than, less than, and the key of each vertex is less than every key value of its right and greater than every key value of its left. Let's see if we can look at it. So, shape of a binary search tree all depends upon the key values and their order of insertion. If you insert J, it starts the tree. So where would E be placed? Well, E would have to be to the left. And where would F? Well, it would be the left of J, but if this is E down here, it would be the right of E. Does that make sense? T is greater than J, and A would be to the left of J and to the left of E. Does that make sense? How about E, A, F, J, T? So E is to the right of A, F is to the right of E, J, so you might, this tree is not really as nice because it's just really a list. Another binary search tree, okay. Add nodes containing these values in this order. D, so D would go to the left, and would go to the left, but it's the right of A. You don't insert in between, it always goes down to the bottom somehow. B, to the left, and then to the right, which is where D is, but then B would go to the left. Does that make sense? So that D and B would be inserted that way. If you put in the L, so L will go to the right, but will go to the left of T. It's to the left of M, but to the right of K. Does that make sense? Is F in the binary search tree? It's not there. You say it's less than J, it's greater than E, but it's also less than H. It would have to be down here. Traversal algorithms, where you go through the tree, is a procedure that looks at every vertex, and it's done recursively, so it's sort of interesting to write that in a program. There are three: pre-order, in-order, post-order. T is the ordered binary tree with root R. If T has only a root R, then it's pre-order and post-order, and in-order is just R. Otherwise, T1 and T2 are the left and right subtrees of R. So then you just go, depending upon whether it's less than R and greater than R. The pre-order would always look to the left. T1, then R, then T2. So, visit this first, and then for pre-order, you visit this one, and then you go down to the left of that, and then you go to the right. Does this make sense? Pre-order. It's really based on the parent. When are you going to look at the parent? Well, you look at the parent first. So it's the root, then E, and then left and right, pre. And then it'll go to the T, and the M, and the Y. So the parent will be looked at first for each of these. Pre-order. J, E, A, H. It's up here. Then T, then M, then Y. In order. Now it does it in order, so it's going to go left, parent, right. Where before it was parent, left, right. This is now left, parent, right. So it's going to go left first, so it goes down the left side until it hits the bottom of the left, so to speak, A. Then it looks at E, so it's left, parent, right. So you always look way down the left, parent, right, which means you go to the left, parent, right. So this goes A, E, H, J, M, T, Y. And post orders when you do the parent last. So it's now left, right, parent.